Okay, let's try another one. So the next one, what we've got is a ball accelerating down a ramp. Now, one thing you want to start listening for is acceleration or constant velocity. If something's accelerating, that means it's getting faster and faster, and that usually means we have unbalanced forces. If it's constant velocity in these problems, that means that the forces are balanced, and we'll get to one of those in a second. Okay, so this one, let's first of all draw the box. So this represents the ball. There's going to be the force down, so that's the force of gravity. Okay, now let's look at all the forces around this ball right here. So first of all, the ball is sitting on an inclined plane and moving down, or a ramp. And so there's a normal force here, but the normal force, remember, the normal force is always going to be perpendicular to the ramp that you're sitting on. And so there's going to be a normal force in that direction. So I'm going to call that the force normal. Okay. Next, the ball is rolling down the plane. And so we also have a frictional force. Now, it's probably not very big, and we also have an air resistance force. Now, those ones, so frictional force and air resistance, instead of being perpendicular, they're actually going to be perpendicular to parallel to the motion. And so if it's a normal force, that's always going to be perpendicular. But in this case, since it's going in this direction, motion's in that direction, our force is going to be parallel. And so I'm going to try to draw, and that's not very good, but I'm going to try to draw a line that's parallel to the ramp. And I could always represent that as the force of friction. And lots of times I'll just double these up, and then the force of air resistance. And so that represents both of those. And those are going to be up the ramp. Now I can't see any other forces acting on it. It's the force of gravity that's causing it to accelerate down the ramp. Okay, let's do another one. Next one we've got a box is dragged across the floor with a rope. So it doesn't tell us much about if it's accelerating or not, but it's being dragged across the floor. And so let me draw this one. First of all, the box looks like this. This is the first box that's actually a box. We've got the force down of gravity. Again, that's one that you can pretty much get used to drawing in all of these. Now it's being pulled at an angle. Let me try to get my angle about right. So it's being pulled in that direction, and we're going to call that the applied force. So we're applying a force, and we're applying a force at an angle. Now there's also going to be forces that are slowing it down, and so those are going to be frictional forces, and so that's going to be parallel to what we're on. And so we're going to have the force of friction, and then we're going to have the force of air resistance as well. And that's it. Those are all the forces that are acting on that box. So let's try another one. Next one, I love ones like this. Next, we've got a golf ball. So we're dealing just with this golf ball right here. And it's just been hit. So the club just swung, it just came by, hit the golf ball, and now it's kind of in flight. And so how do we do that? Well, let's draw the box to represent the golf ball again. So we've got the force of gravity that's acting down on the golf ball. Now, a tendency, I've seen students do this a lot, is since it's moving or it's been hit, the tendency is to put some kind of an applied force on that. But remember, once we've hit it, then there's no force acting on it. And so the only other force that's acting on it is going to be the force of, since it's not on the ground, it's still going to be the force of air resistance. And so it looks like the ball kind of went in this direction, so it went like that. And so I draw my force of air resistance in the opposite direction. And those are the only forces that are acting on it. There's no applied force because we already applied that force, and that's what made it take off. All right. Last one then. This is our last one. We've got a climber, and the climber is rappelling down a rope, and the climber is moving at a constant speed. Okay, so it's not accelerating, so let me draw the object again. So we've got force of gravity that's acting down on the object. And now we've got a force that's going up. So if there was no rope, that would be the only force except for maybe air resistance going in the other direction. But what's slowing you down is that you'll run the rope through a carabiner or through some kind of a figure-8 device, and that slows down the climber. And so it's friction that's actually slowing down the climber. And so we would have the force of tension that's holding it there but it's also the force of friction inside that rope that is slowing it down. And since that climber is moving down at a constant speed, the force of gravity and the force of tension and friction are going to be balanced, or they're going to be equal. And so if you're ever moving at a constant velocity, we can't tell the difference, at least in a force diagram, between that and then just sitting there. In other words, not moving. And so that's one common misconception that we have on free body diagrams. But that's about it. And so I hope that's helpful.